All right, thank you everyone. Welcome to the type system session. So our first talk is from Qiancheng on the PReST system for programming language for randomized distributed computing. Take it away.
Yeah, so thanks for attending my talk. This work was done in collaboration with Professors Ankush and Gaboardi during my PhD at Boston University. So we developed this PReST language for writing and verifying randomized distributed programs. So just a very brief background. So scaling with distributed computing is very powerful, but it's also very hard. We have a whole slew of different kinds of bugs, like malformed data, deadlocks, race conditions, and lossy networks, and just all sorts of normal bugs that skip past us, our human auditing. And a lot of these bugs tend to slip past testing and make it into production. So randomized distributed algorithms can help combat some of these problems. For instance, for the very classical deadlock problem of Chinese philosophers, there's a elegant solution of doing it through randomization. For race conditions, there's various kinds of randomized leader election. And then for lossy networks, we have lots of retransmission protocols like the classical TCP. So randomized distributed algorithms are powerful, but they're also very hard to get right. So it is very hard to trigger and reproduce bugs caused by these things. So this can lead to silent errors, and where programs never crash, but might produce wrong distribution of outputs. And this can lead to very insidious privacy and security risks. So for instance, in the crowd forwarding protocol, which does a bunch of forwarding to anonymize a message, if our forwarding target is not uniformly randomly chosen, then an adversary might gain some advantage and then figure out who it was from, and that will kill our privacy. And this is what led to us to develop the PReST language. So PReST, which stands for Probabilistic Refinement Session Types, it allows for the embedding of probabilistic protocols into types. It has a message passing based form of concurrency and has a probabilistic semantics. And more importantly, it formally guarantees that the runtime behavior of our probabilistic programs actually matches their protocols. So I do want to clarify that this programming language is not a probabilistic programming language in the sense that we don't do inference. The type system more acts kind of like a lightweight program logic that ensures the correctness of our programs. Okay, so what we do is that the PReST language extends the probabilistic session types of Ankush, which was published at POPL. So here we have probably the most simple probabilistic session type that we can have, and it's a probabilistic bool type. So intuitively, this bool, as a channel or a communication channel with this type bool, will have the message true with probability 0.6, or it will have the message of false with probability 0.4. So this type acts as a contract between our senders and receivers. So for our senders, it has access to its own sources of randomization, and it must provably produce a message of either true with 0.6 probability or false with 0.4. And on the other hand, for our receiver, which is receiving this probabilistic bool, it can now rely on this randomness, true and false, as a source of its randomness to generate new probabilistic messages. So the paper of Ankush, so the original probabilistic session type paper already shown that if we only care about a fixed number of participants and a fixed number or fixed probabilities, that it's already very powerful and is able to express a lot of these protocols. However, the restriction of these standard probabilistic session types to concrete probabilities limits its expressiveness in many real-life protocols, which are often parameterized by probabilities or the number of participants. So importantly, PReST generalizes these concrete probabilities to symbolic ones. And that does it through probabilistic refinement session types. So here, we have the new p-bool type, and now it's indexed by a logical variable p, which ranges over real numbers. And we can define it to be in the range of 0 to 1, so making it a valid probability. Now, if we case on this true now, this is intuitively saying that we're going to send or receive a true with probability p and false with 1 minus p. And during type checking, we'll emit a bunch of constraints that says, okay, p has to be a correct probability. Okay, so now we have our types. We also need a primitive source of randomness. So PReST features this flip primitive for generating randomness, and it's very simple. So it just takes in an argument p, and it flips a coin. If it's heads, it hits heads with probability p, or tails with 1 minus p. So given p in 0 to 1, flip lands on heads with probability p, tails with 1 minus p. So now to type check a PReST process, the flip construct will actually interact with these probabilistic refinements. So here we are trying to implement a probabilistic channel using a flip to generate the messages. So here we have a make p-bool function where we are indexing with p, and it's in the range, the correct range, to make it a probability. And then we are emitting on this channel C a probabilistic bool with exactly probability p of landing on true. So we're doing this through the flip primitive. We're flipping a coin, and if it's landing on heads, we're going to send on this channel C the true message. Otherwise, we're going to send false. So the way that we do type checking is that we would actually isolate one of these branches and look at it by itself. So if we don't care about the outer program and we just look at this channel C.true, so this is sending true on this channel C, then the distribution of messages that we could observe if we were the receiver would just be true at probability 1 and false at probability 0, right? Because we're never sending this false message, so it has to always be true. And similarly, for the tails branch, because we're only ever sending the message false, then we would have the distribution of true at 0 and false at 1. However, because both of these actions are inside of the arms of the flip expression, to compute the joint distribution of these two actions, we would have to perform a weighted sum of these. So the overall probability distribution that we would observe from this flip expression would actually just be the weighted sum of these, which is true at p and false at 1 minus p. So what our type checker then does is that we will synthesize a big SMT formula that constrains that, okay, the thing that we are going to observe on this flip, the distribution we're going to observe, actually matches the contract of the type. Okay, so now we've seen the basics of using PReST. I want to talk about modeling probability distributions in PReST. So many randomized distributed protocols require sampling from probability distributions. For example, in leader election, we have to sample from a bunch of candidates. In crowd forwarding, we have to uniformly sample from a big number of crowds, or big number of crowd participants. And in zeroconf, we have to uniformly sample from a IP address space. So how can we accurately state this through our protocols? So it seems we have a conundrum when we are faced with these sort of parameterized protocols, that we have to somehow encode a parameterized distribution like uniform 0 to k. And it seems that we are doomed to extend our language with some n-ary primitive, which will actually dramatically complicate the underlying theory. And this is because, so our flip only has 2 branches, and our probabilistic types have only a fixed number of branches. So how do we resolve this? So it's very fortunate that the parameterization actually saves us from this. So the key idea is to let probabilities and refinements interact with each other. So here we have a UNAT encoding, so UNAT as in uniform net. So intuitively it is trying to model a natural number uniformly sampled from the uniform distribution 0 to n. So this is a unary encoding of a natural number using session types. So the idea is that we're going to send a number of successor messages, and that number of successor messages will be the encoded number. The important thing to notice in this UNAT encoding is that the probability of us sending successor or 0 is actually controlled by the logical parameter on the type. So the successor has probability n over n plus 1, and 0 has 1 over n plus 1. And this will actually change as we start to unfold this UNAT type into a big trace of successor messages. So to see how this works, let's actually unpack a concrete instantiation of this. So let's say UNAT 3. So we would observe the 0 message, or just a single 0 on this 0 message on this channel. And this gets out with probability 1 over 4, because if we substitute 3 into 3 for n, we have 0, 1 over 3 plus 1, which is 1 over 4. And we would have the message trace suck with 0, which is encoding 1, with probability 3 over 4 times 1 over 3. This gives us 1 over 4. For suck 0, which is 2, we would have a similar expansion that gives us 1 over 4. And then finally, for 4, we also have 1 over 4. So now we've seen, for at least a concrete example, that UNAT 3 indeed does encode a uniform distribution with, over the traces for 0, 1, 2, and 3. So now, what we would really like to claim is that UNAT n encodes the uniform distribution over 0, 1 to n in a very general way. So the good news is that we actually have something concrete now, and we can try to verify this out by hand using induction. The even better news is that we can automatically verify this using the PReST type checker itself, and this was very surprising to us when we first discovered this. So what we discovered is that refinements allow us to encode what we call a probing process to measure probabilistic properties. So here we have a UNAT PMF function. So the idea is that this function will take in a uniform natural number x, which ranges over 0 to n, and just an arbitrary natural number y, which is also selected through between 0 and n. So the important thing to note about this is that x is random, whereas y is arbitrary, but it's fixed. And all this UNAT PMF function is doing is it's doing an equality comparison of x and y. So it's going to return true if the number of successor messages it observes on x and y are the same, and it will emit false if it sees something different. So this is actually just doing what the probability mass function is doing in math. And we can see that through type checking, it actually verifies that our true message, which is the probability that our x and y are the same, is exactly the probability mass function that we would get in math. And this is another very surprising thing is that this entire UNAT PMF function is completely static. We don't need to run it at runtime, just by the fact that it type checks tells us that our UNAT encoding is indeed correct. And we can do this for even more complicated distributions. So one of the things that I tried doing was to do it for the maximum of 2 uniform distributions. I basically just had ChatGPT tell me the mathematical probability mass function. I copy and pasted it in, and I type checked. So now that we've seen how these distributions can be encoded, we can actually use these as building blocks for more interesting and more real-world facing protocols. So here we have a protocol for, or part of the protocol for a crowd forwarding protocol. So here we have a packet, which is essentially a type that's encoding a tuple using session types, and its layout is a message, a forwarding target as the second natural number, and then a final destination as the last natural number. And then for our R packet, it is a randomized packet, which is sending to a random forwarding target. So this it would be encoded as a UNAT. So the first thing that our node in the crowd is doing is that it is receiving a packet. And then depending on whether this packet is intended for our current node, it will either forward or accept in a provably sound way. So if it is intended for our current node, then we would accept and the protocol would end. Otherwise, if it's not provably the current node that's destined for this current node, we will repackage it as a random packet and then repeat the protocol. So now for our meta theory. So we prove that PReST possesses the following properties. It has type safety, that evaluation of PReST programs preserves types. We have global progress, where everything is guaranteed to be deadlock-free. We have probability consistency, that the distribution of communicated messages at runtime match the specification of probabilistic types. And we have an expected cost bounds theorem, which I didn't show today, that says the expected runtime cost of a program is upper bounded by its cost specification. So this is an extra annotation that we can add onto our types that tells us how many iterations that a function will run for. So for our implementation and evaluation, so the PReST type checker is implemented in OCaml following a bidirectional type checking strategy. So logical and probability constraints are generated during the type checking process, and they are exported to Z3. So the the constraints that we generate are using the nonlinear real arithmetic theory. So they are quite difficult to solve. So we evaluate PReST on a wide array of benchmarks. So we notice that despite the nonlinear real arithmetic constraints, Z3 performs very well, and all benchmarks are solved within 0.3 seconds. However, sort of the caveat to this is that this SMT solving is a bit brittle. Adjusting how these constraints are generated and encoded can sometimes blow up the solving time. We also notice that CVC5 is not as robust as Z3 for solving PReST, and that our constraint solving time does not necessarily scale linearly with our program size. For example, our Umax encoding solves very quickly, even though our Umax encoding takes a quite long time to solve when compared to our consensus coin protocol, which is much longer, but it takes less time. So for our future work and conclusion, so we want to apply this to reason about cryptographic protocols and differential privacy. We want to improve our constraint solving expressiveness and automatic solving with more relaxed notion of satisfiabilities. So such as we want to incorporate the D-real solver. This will make our probabilities a little bit less precise maybe, but we might be able to bound the loss of precision there. And also we would want to integrate ideas from probabilistic program logics. So with sort of the recent momentum on this front, where a lot of work is done in probabilistic iris, I think it might be also interesting if we can integrate ideas from these probabilistic session types into these probabilistic program logics. So in conclusion, we developed PReST for specifying and constructing randomized distributed systems. The integration of probabilistic and refinement types allows for a rich specification language and symbolic reasoning about protocols. PReST programs are formally guaranteed to behave according to their protocols, and a type checker for PReST is developed and evaluated on a variety of benchmarks. So the PReST type checker performs very well on many of these randomized protocols. So thank you.
Okay, thank you so much. We have time for one question while the next author goes to get his microphone. Yes.
Hi, really cool results. Do you know if PReST can be used to define sound generators for arbitrary inductive and co-inductive types? Because you showed the example for UNAT.
Yeah.
Do you think PReST can be used to do it for any inductive type?
I think so.
Like the user would just have to define
yes.
a sound generator and it should work.
Yes, I think so, yeah. Because for PReST, we actually have full general recursion, so I think everything should work.
Cool.
But it might not be sound as a logic anymore.
Sure. Okay.
Yeah.
Thank you.